The paper is devoted to the up-to-date state and recent trends of neutron diffraction at pulsed neutron sources. Pulse sources have been under active development during past decades and open new perspectives for neutron scattering. One of the unique pulse sources, the IBR-2 pulse reactor, is operational at the Joint Institute for Nuclear Research in Dubna. Examples of scientific studies performed at the IBR-2 reactor are presented in this review. Viktor Aksionov is corresponding member of the Russian Academy of Sciences, Science Director of the Konstantinov Petersburg Nuclear Physics Institute, and Chair of the Neutron Scattering Department of the Moscow Lomonosov State University. Anatoly Balagurov is a professor, chief researcher at the Joint Institute for Nuclear Research, and professor of the same department. Pulsed neutron sources provide a natural possibility for realization of the time-of-flight technique for analysis of neutron scattering. The principles of this technique are rather simple. Neutrons with a continuous distribution of speed emerge from the source after a pulse. They travel some distance and arrive at the detector at a certain time. The respective wavelength related to the neutron speed in a simple manner is readily calculated. Thus, measuring times of flight, one can find the distribution of neutron intensity as a function of wavelength. The first experimental realization of the technique was performed in 1963 at the first pulsed reactor IBR-1 in Dubna under the leadership of Professor Bronislaw Buras from Poland and Professor Fyodor Lvovich Shapiro. The second pulsed reactor, the IBR-2, was put into operation in Dubna in 1984. At IBR-2, the new diffraction method, high-resolution Fourier diffractometry, was realized in 1992 by a collaboration of physicists from Dubna, Gatian, and Finland, led by the authors of this review. High-resolution Fourier diffractometry, developed in Dubna, allowed to perform a number of high-level studies of the structure of new materials with unusual physical properties. One example is presented in the slide. It concerns the mercury-based high-temperature superconductor discovered at the Moscow State University. The atomic structure of this compound is shown in the slide. The upper picture to the right shows the high-quality diffraction pattern measured with the high-resolution Fourier diffractometer at the IBR-2 reactor. After mathematical processing of this pattern, the interatomic distances were obtained with a very high accuracy. Lower picture. At present, the Fourier diffractometer is actively used in studies of structural transformations inside the electrodes of lithium-ion batteries during the charge-discharge processes. In the upper picture to the left, a 2D representation shows the evolution of diffraction patterns during the 3 cycles of the charge-discharge process in a commercial lithium-ion battery. Changes in the intensity and position of the diffraction peaks are associated with the migration of lithium between battery electrodes. Analysis of these changes provides a unique insight into emerging structural phases, the kinetics of their formation and decay, their fraction in the electrode volume, etc. In this slide, a summary of the main conclusions of the paper is shown.